Stanford University.
Good evening, everybody. Welcome to the spring quarter edition of the SIPP mini courses. Each quarter we try to bring you one of our SIPP, Stanford Institute for Theoretical Physics, one of our leading, eminent theoretical physicists, to tell you what, basically what they find interesting, what they're excited about, where they think physics is going. The level has largely been somewhere between Scientific American and a physics colloquium, but I basically tell each professor, you don't tell professors what to do. That's a rule, you don't tell them what to do. I do tell them, do what you want to do. That's hard to fight with. In any case, tonight we have Eva Silverstein. 25 years ago, I think I must know you for almost 25 years now.
Yeah.
Hard to believe it.
It is.
Right. 25 years ago, Eva was one of the young people who became very excited, enthusiastic, inspired by string theory, and she very quickly became one of the leaders of the field. She's produced a singular body of accomplishments and work in the field, almost every area of it, and well beyond the field of string theory. In fact, she occupies a rather unique place in that a few years ago she recognized the possibilities inherent in string theory in asking and answering some of the very hard questions about cosmology. And today, people all over the world are working to find out how to test some of her ideas. Eva is a spectacular star in the field of theoretical physics, covering many areas. And if I had to guess, I would guess that's not what you're going to talk about tonight, inflationary cosmology, but I'm not sure.
It's in there.
It's in there too. Okay, but the main point is, Eva, tell us what you think is exciting.
Thank you, Lenny, for that incredible introduction, incredibly kind introduction. I'm very glad to be here. I've admired Lenny's efforts at what we like to call night school, which is not a pejorative at all. It's a wonderful thing, and I'm glad to finally participate myself in this. I do find inflationary cosmology exciting, and it will be part of the story. But the theme of these lectures will be unified by the notion of a horizon. This is probably something everybody's heard of. It's basically a boundary of a region from which not even light can escape. And what I'll do is I'll start by describing how this comes about in our classical theories of space-time physics. I'm going to start with a Pythagorean theorem, and then hope to get to the origin of all structure in the universe in these lectures. So we'll see how well it goes. By the way, please stop me with questions at any point. I'm only using PowerPoint because, as you'll see shortly, my writing is atrocious, but I am very happy to write on the board and engage in discussion. That's a large part of the point. So the plan, as you can see, is to start from the basics to explain what this notion of a horizon is in our classical theory, and then move to our goal, which is to discuss two very important examples of this in real physics, which are also very interesting and challenging still to us theoretical physicists. And this concerns, the two I have in mind are the horizons that arise in cosmology, in inflationary cosmology, where we get from them, first of all, a beautifully simple theory of the origin of structure in the universe. But even given that, if you dig a bit deeper, you find that it's sensitive to what we call quantum gravity in a way that I want to lay out very carefully for you in these lectures and discuss some of the very interesting consequences of that, which include, believe it or not, a role for string theory and really its spin-offs in empirical science, which may surprise some of you depending on what you've heard in sort of the public discourse about string theory. But one of my goals here is to explain that carefully. And the other place which continues to amaze and puzzle us theorists is in the context of black holes. So both of these, as I say, are observed in nature, somewhat indirectly, but spectacularly, and also challenge us in theoretical physics. So let's get started. So before I get to the Pythagorean theorem, let me just flash what probably many of you have seen, at least at this cartoon level, that we have a theory of classical gravity due to Einstein that's now over 100 years old, in which there's a set of equations that basically relate the geometry of space-time, and we'll discuss more about what that means, to matter sources, matter and light, energy and pressure, so to speak. So there's some set of equations that, roughly speaking, in quotations, we would write as curvature equals energy. And the two targets for our investigation are these extreme situations where you have matter that's so dense that, according to this equation, it curves space into a black hole with an event horizon beyond which, classically, nothing can escape. The other case where horizons come in, importantly, is in cosmology, where the right-hand side of this equation is a homogeneous source of energy, that it's homogeneous in space and nearly homogeneous in time as well. And that turns out to source an expansion of space that accelerates. And in that context also, we obtain a situation where different observers lose causal contact with each other. But let's go back to some basics that will help us understand what this means. So some of the principles that we start with in space-time physics classically are the following. So nothing moves faster than light. Particles that aren't subject to any non-gravitational forces will, if they're going from A to B, they'll go straight from A to B. They'll take the shortest path. So we're going to start discussing, even though we're interested in these curved geometries which have this property of generating horizons, let's start more simply with flat space-time. So there's no matter or radiation causing any curvature to begin with. But actually, let's start with just space. And let me indeed start with this equation that I think everybody knows, that the square of the length of the hypotenuse of a triangle in flat space is equal to the sum of the squares of the other two sides. Now, let's also notice that we can take this picture in this equation and we can rotate it, we could shift it around in space, and it won't change this relationship. Right? If I rotate the triangle, it's still true that the length of the hypotenuse is given by this equation. Okay. Now let's include time. And what we're going to do, for reasons that I'll lay out slowly in the next few slides, is to take this interval that was so far in space just labeling the length of the hypotenuse of the triangle, and let's do that, add also some other dimensions of space, three total dimensions of space, but also add in time, and we're going to include a negative sign there when we write the analog of the Pythagorean theorem for space-time. In these equations, I've written the speed of light, c, which in natural units takes this value. And one of the important principles of physics is that this speed of light is constant, it's invariant, it looks the same no matter what frame of reference you move in. So if I boost, so to speak, this picture, massive particles will start moving at different velocities, but light will always move at the same velocity. And we can understand the reason for this minus sign as related to that in the way I want to explain next. But the basic picture here is space and time, and light is along this 45-degree line with a velocity that is c, the speed of light, and massive particles move more slowly than that, and they move along straight lines if they're not acted on by some force. Okay, so let's unpack this idea of a boost, which means to move relative to the original frame of reference. And let's work with this so-called line element. So I've written a delta here as difference, like we had in the Pythagorean theorem. I'm now going to start to use some of the notation that we use in physics normally, which is to replace that by a d, a little d, but it's the same idea. So we have, if we just keep track of one direction of space as well as time, one way to think about this is to write this displacement, this ds, this so-called line element, in this way. So just complete the square, and you see that this is the same as that. If you just use high school algebra, multiply it out, and you get the same thing. But then you can group it into this dx plus and dx minus. And there's an invariance of this equation of the right-hand side that we can immediately see once we write it like this, which is that we can stretch x plus by some amount lambda. We can just multiply it by some number lambda. And if at the same time we multiply x minus, the thing it multiplies in the line element by the inverse of lambda, then the line element ds squared is invariant because we just took it and multiplied lambda times 1 over lambda, which is 1, and we get the same thing back. So we'll see in the next slide why this has to do with boosting, moving relative to the original frame of reference. Right now, it's just a little mathematical invariance that you can see from these equations that fixes this generalized distance ds squared. So, so this ds squared is invariant, as we just saw, under this operation. And also the light cone, which in this language is either x minus equals 0 or x plus equals 0 or both, is invariant. And remember, that was the thing we wanted from our theory. The principle we started with was the speed of light is invariant. Everybody sees it as the same value. And the analog of the rotations of the triangle in this original picture and so on turns into the invariance under the operation that I just described, which in particular fixes the light cone. Okay. So far, so good. Are there any questions?
I just want to verify that d is a differential?
Yes.
Or a derivative?
It's a differential. Just think of it as a little tiny difference. Thanks. Any more questions? Please do ask. Okay. Okay, so let's play with this a little bit more. Let's take the ratio of dx plus to dx minus. And dx plus, so just by dividing the top and bottom here by c dt, we get this is the following thing, which we now recognize as 1 plus dx dt, which is the velocity divided by the speed of light on top, and on the bottom, 1 minus the velocity divided by the speed of light. So what happens when we do that operation that I just described is that this ratio goes to lambda squared times itself. And so the new ratio, 1 plus v prime over c over 1 minus v prime over c, v prime just meaning the result of doing this operation, is given by this. And the thing to notice about this is, so we said that the speed of light is going to look the same in every reference frame. And that means we can't just add up velocities the intuitive way. And this tells us how this transformation to moving frames really works. Now, if the velocities are small compared to the speed of light, so if this ratio v over c is tiny, then we can simplify, this formula simplifies. And if I just it's not essential, but we can take this rescaling number lambda that I introduced and write it as the exponential of something that's small, so this lambda is very close to 1. We did very little to the system. Then this thing does boil down to v prime, the new velocity, is just the old one plus some shift. But if you go to speeds close to the speed of light, you see that it's very far from that, and the speed of light is a limiting speed. So nothing moves faster than light. These equations reduce to the intuitive addition of velocities when they should, but they generalize that to a system of transformations that makes sense, and that realizes this principle that the speed of light is invariant. Okay, the reason I'm dwelling on this, aside from the fact that it's beautiful physics, and it's basically learning this at an impressionable age that got me into physics originally, so I always share it when I can. The other reason to dwell on this is the fact that these horizons that we're going to be interested in have a lot to do with the finite and constant speed of light. So do ask if you have any questions.
It's called special relativity, isn't it?
It is called special relativity. I suppose I should, yes. Okay, so now we're going to go toward our goal of thinking about these curved spacetimes, ultimately related to this theory of gravity, where the curvature is related to the energy and so on. And what we're going to do then is take this line element, this ds, and allow it to have, and write it in terms of the differentials, these small displacements in the various coordinates, time and space, but allow the coefficients in that to vary with time and with space. So we write, the names don't matter, but we write this line element with such coefficients that are allowed to vary. I've drawn here a patch of a curved space where one of the tools we can use is to think about it both globally but also locally, where it looks approximately flat. And by patching together approximately flat local patches, which work like in special relativity, we can obtain the more general theory of what's called general relativity to deal with these varying coefficients. Now, one of the important features that we just discussed of special relativity is the invariance of physics under the laws of physics under boosts and rotations and so on. And also, in general, the physics is invariant under exactly how we parameterize the directions in space-time, this t and x and so on. So we can change our parameterization of those directions without changing physics. Okay, so in a locally flat frame, we just go from A to B in a straight line. And there is a theory of minimizing our distance in a curved space-time by basically tracking these flat space regions that appear locally. And within each of those, the system goes in a straight line. Altogether, the motion is on what we call a geodesic, which is the shortest distance in the curved space-time geometry. It's essentially taking this line element and finding an extremum of it. So we minimize the distance, basically. No discussion of special relativity and its patching to general relativity would be complete without the equation E equals mc squared, which sits here. So the energy is related to the momentum and the mass in this way, locally. And the momentum, which in classical physics that you might have learned in high school would just be mv, has this extra piece that blows up as the speed of light is reached. And similarly for the energy. Okay, so just a little tangent on what we mean by curvature a little more formally. So one thing to keep in mind is that although it's convenient in our minds to think about some surface as embedded in a higher dimensional space, the notion of curvature that we are using, that we're interested in, is an intrinsic one. It doesn't depend on an embedding into higher dimensions. So for example, if you take, it's basically a measure of how, if you have one of these line elements with these general coefficients, as you move around, the lengths change. And it's basically how the change in the lengths change. It's a so-called second derivative of these coefficients that describe how the line element varies in space and time. Here I've just written it in a two-dimensional space, but the idea is more general. And in space-time, bringing time back in, a nice way to think about it is that curvature can take two initially parallel trajectories, which would just always stay separate from each other in flat space-time, and cause them to move apart or move together. And we'll be particularly interested in this picture I flashed earlier, where the space-time is undergoing an exponential expansion, and the trajectories move apart so dramatically that they lose contact with each other. Okay, so that's the kind of distinction that we want to get to. In flat space-time, if you think about it, an observer, that's my script for an observer O. If they wait long enough, they can capture signals in light, labeled by this label gamma, from anywhere if they wait long enough. So, like if this observer only waits for up to this time is running upward in this picture, then they don't see what's out here, but if they wait longer, they do. And you can easily convince yourself that everything is in causal contact in flat space-time. However, if you inject an infinite amount of energy and accelerate some observer forever, then they can actually lose contact with light rays from other parts of the space-time. That's a bit artificial because it does take an infinite amount of energy to do that, but it's worth keeping in mind. As I say, we'll be interested in the situation where the curvature of space-time, which is sourced by matter and energy, does that for us. It's not an artificial thing. It's automatic. And probably the easiest geometry to think of that does it is the case of actually real-world interest in cosmology, very early universe cosmology, where the space expands exponentially. Okay, and here's, I've been saying that in words, but here's the line element, the ds corresponding to that. We write ds squared as minus dt squared. I'm dropping the c now. This is something we professionals do because we're lazy, but we remember how to put it back in. And then we have the part that comes from the three directions of space, but the coefficient function is growing exponentially in time. Okay, so that's a relatively simple version of this thing where we can sprinkle in these space-time dependent coefficients. And this exponential function means you multiply by a certain number as you shift in time by a certain amount, you multiply by a number greater than 1 each time. So it's exponential growth, which I think is probably familiar to everyone, but ask otherwise. So in that situation, the observer just gets moved along in the space-time. If they just sit there, and I should have drawn another one nearby, say this one goes that way, this one goes that way. They're just sitting there in the space, but they get pulled apart by this exponential expansion of the space as a function of time. And so they lose contact. This ray of light just can't get there. By the way, I should probably emphasize that this question of whether there's a horizon actually depends on what happens in the asymptotically far future, which none of us know. So it can be a notion that kind of arises approximately or for a finite time, but it's a little bit, mathematically, it's only really well defined if you know it's going to happen arbitrarily far in the future. but it's still a useful notion even in the real world where we measure things over finite time periods and so on. And I'll try and make that clear as we go on. Okay, so this is the first and probably easiest example. Are there any questions?
What's the coefficient you have on that T?
Oh, good. Thank you for asking. So this is just a parameter. It's called Hubble, and you can think of it as, well, let me actually, there's a slightly more general way that we write this kind of line element. So let me do that. So ds squared equals minus c squared dt squared plus a of t squared dx squared plus dy squared plus dz squared, right? Now what I took here is a of t equals e to the ht, and h is here meant to be a constant. When it comes to this early universe inflationary theory and beyond, we will discuss what we know about this, but for now just take it to be a constant. It has units of energy or inverse time, inverse time. And so just to anticipate a little bit, we have a lot of evidence that there was a phase like this in the early universe. And this parameter h could be as high as the so-called grand unified scale, which is 14 orders of magnitude higher than the scale of particle physics that we measure directly. But it was that big long in the past. That's what I was saying. Yes, in the very early universe, we don't know how big it was. There's a range. So I'm going to discuss this quite a bit, but for now it's just a parameter. In fact, pretty soon we'll get to one of those Einstein equations that determines it. So I'll write that down for you. And since we're on this topic, I could also say that there's a more general version of this where there's a function, h as a function of t, which is the time derivative of a divided by a, or in our normal notation, a dot means a time derivative. So more generally, there's a function Hubble that describes a more general time evolution of this expanding space. And you'll often see h of t, which means a dot over a. Now you see why I'm using slides, but I hope that helped. Are there any questions? Yes?
Why does the light not curve in that direction?
Oh, well, the light it follows what it does. So the correct statement of what the light does is that it always has this ds equals 0. So it's possible that I didn't draw it correctly in this diagram. We often make a transformation in which it's always going at 45 degrees, but the equation it solves is ds equals 0. Any other questions? Okay. Okay, so we were already doing this. Wait, I just went.
Actually, I do have a question.
Yes.
I'm struck by the fact that the Rindler horizon requires infinite energy,
Yes.
whereas in an expanding universe, you don't need infinite energy.
Well, in some sense you do, but it's just distributed over all of space. So it's infinite because you ultimately have an infinite volume. You might always have, it depends on the topology of space also, but right. Well, one way to say it, I think, to get better at your question is, suppose you were trying to work in flat space-time, but then you injected all this energy to make this observer accelerate, well, then at some point, you better include the effect of that on the geometry itself, for example. So you have to be careful about things like that. Having said that, there's a sense in which the horizon very near a black hole is like a Rindler horizon in the sense that for an observer to stay outside of it, they would have to accelerate. But the curvature of the geometry makes a difference, and we'll get to that. Okay, in fact, we were coming to this on the next slide, which I can now show you. So here I'm just sharing with you a little bit more of the detail of this curvature equals energy type equation. It's actually a set of equations, but one of them is one that determines this function h of t, with that being the left-hand side related to the curvature, and the right-hand side is the energy density in units of a fundamental constant. It's called the Planck mass, which, putting in all the constants back in their full glory, is it squared is inversely related to the Newton constant, the thing that determines the gravitational force. In terms of energy scales, it's gigantic. You can also think of it as the mass of the lightest black hole, and I'll say more about that later. But anyway, the equation that generates A of t through this equation does have this exponential solution. A is some constant times e to the ht, if the right-hand side is constant. If it doesn't vary in time or in space, which I've assumed here, that it doesn't vary in space, then we get this exponential as a solution. So this is kind of a global picture of that space. Again, light rays have 0 ds. And you can ask how to think about the physics just in a patch of the space-time that an observer has full access to. Now, I'm not going to answer that on this slide, but what I want to show you, and I haven't derived this for you, I'm just writing yet another formula for a displacement ds, and you'll see the pattern as we go. But it turns out that if you take, so before, remember I emphasized that with these formulas for ds, like this one, it doesn't matter how you parameterize the space and time directions. You can redefine them and still get the same physics out. And there's a redefinition, which I'm not explaining, so don't feel like this formula should be clear to you. I'm just going to tell you that we can make such a redefinition of variables that we use to describe the system, and characterize the patch that a single observer can see in this way. And it has a certain, so the direction r is horizontal in this picture, basically, and the direction t is the time direction. And you can see that the coefficient here goes to 0 at some finite value. And that is where the horizon sits. And I'll say more about that momentarily. After flashing for you a similar line element, a similar formula for this ds that applies to the black hole case. And again, there's a radial direction away from the object with these coefficients that depend on the position in front of the coordinate displacements. And again, in this case, there's a coefficient of this time direction, which goes to 0 at a special value, and that turns out to correspond to the horizon. I'm going to say more about that shortly, but for now, I hope this at least fits within the framework that I've been trying to introduce to you with these formulas for ds. And this is just a nice way of characterizing the horizon in a set of variables that are kind of natural for an external observer. Okay, so for black holes, there's a lot to say, and we will not be able to say all there is to say about them. And even if we did say all that we could say about them, there are huge puzzles that remain. But let me just make a few comments. These black holes are formed again by matter coming together into a very dense region so small that a horizon forms and light cannot escape. And one funny feature of them, which you can sort of see from this formula that I am flashing for you, is that the result of that doesn't depend on the details of what the matter was that went in. It just had to be dense enough, and then you get this very simple geometry. But there's a lot of evidence that this is just a very macroscopic, a kind of coarse-grained description. And there's a lot of facets to that, but just at the level of the fact that you could have formed it in many ways sort of should clue you into that. And we're going to start when we get to applications with the cosmological case, but we'll come back to the black holes given time later on. Okay, so this, so we saw this pattern when I wrote for you these formulas for ds near horizons. Let me flash again briefly. There was the one in an observer patch in cosmology with this funny coefficient, and the one in black holes. And with yet another simple coordinate change, we can actually write it near the horizon in a simple way as a displacement in time times some function that goes to 0 at the horizon, but goes, well, actually in these well, it goes to 1 far outside, plus just a simple displacement in the radial direction. And one thing you can see from this is that there are different notions of time. So if you count time with a clock corresponding to this variable little t, and you compare it to the time counted on a clock carried by, say, somebody who falls into the black hole, whose radial displacement is 0 because they just are at their own position, then there's an infinite factor, an infinite ratio of those two notions of time. So one way to say this is that the clock of an observer far outside ticks infinitely many times as somebody falls into the horizon. Another feature of these horizons is, as you could guess from the fact that light doesn't escape from within them, is that the escape velocity for anything is the speed of light at the horizon. So this is all very dramatic, but on the other hand, the curvature turns out rather mild, or can be rather mild at a horizon. So here's a picture of that. Let me start with space again. Well, actually, let me start with the space-time. So I had these coefficients in the line element, and I said it went to 0 at the horizon. If you work it out, it goes to 0 like a quadratic function. It goes to 0 in a fairly simple way. And this line element describes a geometry which actually doesn't have any curvature. The corrections to this that pertain further away from the horizon contain the curvature in the problem and affect how things fall into the horizon in a big way. But when you get close enough to the horizon, it might as well have been Rindler space. And it's not curved. Now, there's a spatial version of that that's maybe a little bit easier to understand. If you take a sphere, like what I've drawn here, the line element for that is simply d of theta, the angular direction in this direction, starting from the North Pole, plus a coefficient that's just a trigonometric sine function squared, multiplying the displacement in the phi direction, this angle. Now, it's just a simple feature of this. Don't worry if you don't remember your high school trig, but basically, this sine function goes to theta itself as theta becomes small. And what that describes is simply that these circles in the phi direction are getting smaller and smaller. So even though there's this vanishing of this coefficient in the spatial case, this coefficient of d phi is getting small as theta goes to 0. You can see in this picture, all that's happening is you parameterize things with these circles that are getting smaller and smaller, but it's a flat space. Nothing really funny is happening there. And this thing with horizons is quite like that, just in the space-time case. Are there any questions about any of this? Okay, so this is a great subject because it has it all. It's very interesting theoretically. I hope that's already clear in the classical theory that I have tried to outline. And it gets much more so when we include more aspects of modern physics, like quantum theory. But another very important feature is that these are real. These things are seen in the universe. So black holes are now seen in a variety of ways. It's always indirect by definition. Nothing can come out of the black hole. So this top thing, I'm not going to belabor this too much, but I think I'm not an observer, and it would be a stretch for me to tell you all about it, the details of these things, but they're beautiful measurements. So this top one is a picture of orbits of various bodies in the vicinity of what is thought to be a black hole in the center of our galaxy. And these guys studied that for over a decade, and it all fits with it being a black hole. Recently, there was a spectacular discovery of a gravitational wave signature of a pair of colliding black holes. At least, again, the measurements are quite consistent with the general relativistic predictions for that process in a lot of detail for some black holes that are inferred to have masses that are 30 times the solar mass. There's another project going on called the Event Horizon Telescope, which involves emission from black holes which have matter around them, more like the one in the center of the galaxy and so on. And so it's just a beautiful subject at the observational level. In cosmology, we also have spectacular evidence for the kind of accelerated expansion that I introduced. This is thought to occur both in the late universe, the phase we're getting to now, and the early universe, which I'll focus on in the cosmological part of these lectures. And so in the late universe, there was a spectacular discovery around 1998, where a bunch of different probes, including supernova observed at far back in the universe, and also measurements of something we'll talk a lot about, the microwave background radiation, and other probes, which all fit with a geometry for the evolution of the universe that requires a non-zero constant Hubble in the late universe, a very small value in that case. In the early universe, we'll talk a lot about this radiation, which comes from the time when atoms formed. And we'll see how there it fits also with a period of exponential expansion at a much higher rate in the early universe. So these are just kind of pretty pictures, which I'll get to explain a bit of this one as we go. For those of you who came to Leonardo Senatore's lectures, I think this should build from them. And I think if you were there, you have learned a lot about this already. But I won't assume that either. So, okay. So, so far what I've tried to share with you is the classical theory of special and general relativity, just an introduction to how that works, and with an eye toward how these horizons develop and what they mean. We're going to be interested in, as I said at the beginning, in these systems as probes of higher energy physics. And before moving on, what I would like to do next is explain a very basic feature of modern physics that will come into our discussion, which has to do with when it is that very high energy physics, like the theory of quantum gravity, or just additional particles that might be in the universe at higher mass scales than we have observed, how that fits into our way of organizing physics and observations and theories. So this is something I want to go through very slowly, and so definitely ask me questions if any of it is unclear. Let me start with a cartoon of the energy scales in some aspects of particle physics and gravity that we know about. So we have this very low energy density that is of the order of the source of accelerated expansion that I mentioned that we know about in the late universe. So this energy scale is like 10 to the minus 4 electron volts compared to the 10 to the 19th electron volts, sorry, times 10 to the 9 of the Planck scale. So there's a gigantic ratio of energy scales that we talk about in physics. What we've measured in particle physics kind of goes up to 100 of these giga electron volts, which is 10 to the 9. And that's been beautifully measured. I think Savas Dimopoulos may have given some lectures on that subject earlier in the series. If we go up to the Planck scale, we start to get into a mass scale or an energy scale at which we can get these black hole solutions in relativity. And then as we go up in mass or energy, these solutions actually get larger. They get larger in size to the point where we can start to measure them using the tools that I described just a few slides ago. So in some sense, we measure down here, we measure up there, and we don't know what we have in the middle. So clearly, there's various interesting but still speculative conjectures for what kind of physics might complete our picture of particle physics and gravity, involving ideas like grand unification or string theory, which is going to be one of the tools we'll use in these lectures. And again, as we go to higher energies, we go up in this plot for a while as we do that until we get to this Planck scale. We're also going to shorter distance scales. It's like waves of higher energy have shorter wavelengths, but eventually we cross over to where we go again to longer distance scales and we start to have some handle on it. But anyway, we clearly have ignorance of this wide intermediate range in this plot of energy scales in this plot. Okay, so that might make it seem like, how do we ever do anything? That we have so much ignorance of physics over a range of energy scales that might matter for the observations and theories that we deal with. Well, there's a simple way of understanding why most of the time that's not a problem, which is known as, the names don't matter again, but this is known as Wilsonian effective field theory. And you can formulate this in a variety of ways. It really came out of condensed matter physics, but I'm going to describe it in the following way, which is a little more tied to observables we might consider in gravity or particle physics. So basically the idea is you can take any physical quantity that we think about, measure, for example, the force between two masses, or a probability for scattering of different particles. And we can parameterize our ignorance of the physics at relatively high energies in the previous plot in a very systematic way. So we can take the formula you probably know from high school physics, which is the force is minus g Newton times the mass of the first thing times the mass of the second divided by r squared, right? This is, everybody learns in high school physics. But for all we know, that's just the first in a series of contributions to the force that could come in with coefficients that go inversely with this huge Planck mass scale, for example, or really any of the similar comments would apply if there's other scales of physics, such as grand unification scale or the scale of a tension of a fundamental string, et cetera. But if we just put in the scale we infer from gravity, we would still expect, with coefficients C1, C2, et cetera, that we don't know, that there could be corrections to this expression for the force. And the point is, we wouldn't know one way or the other if they're there. Our observations are not sensitive to that at long range or low energies. So there's something called dimensional analysis where we can parameterize these corrections. We can simplify the form that these corrections can take by noticing that they better not have any net powers of lengths or energies in them. And that's why we get ratios of the Newton constant to the radius of separation of these two objects in my expression with coefficients that are constants. So if you think about it, there's an infinite sequence of terms like this that we know nothing about. But it's okay because much of the time our observations are limited to long distance scales, large values of this R, this separation that appears in this system. And so we don't know these, but we don't need to know these. So these terms are hence called irrelevant in the parlance of this idea of effective field theory. So and for many purposes, that's just perfectly good, and it's a great way of organizing our understanding of physics, starting from low energies and parameterizing carefully our ignorance of higher energy scales and the effects that has. Okay, but there's a caveat here, which is several versions of a caveat here, which is really interesting and comes in early universe cosmology and also we think in black hole physics in a certain way. So again, I want to dwell on this. Let me start. So the idea is that although there's this expansion in these infinite sequence of terms, which are typically very small at low energies, if we wait long enough, if we have a process that goes on for long enough time, and or we have enough data, then we could be sensitive to those things, even though we don't directly excite anything at those energies. So a classic example of this, which again, I'm not sure if for those who went to Savas's talks, I imagine he might have talked about this. I'm just going to say it very qualitatively. There's this idea of grand unification, which if it happened at a very high energy scale. And just a couple of orders of magnitude below the Planck scale. This theory, in its simplest form, predicts that there are particles at that scale, very heavy particles, and these are not things we've produced in accelerators. However, but they could participate in particle interactions. And the theory predicts that they do, and in fact that they would cause the proton to decay. So what experimentalists did is they said, okay, well, if the proton decays, I could see it if I assemble a huge amount of material containing protons and monitor it for a long time. And even though the process is small, it's one of these things that appears in this sequence of suppressed terms. If you have enough chances for it to happen, it could happen. And conversely, if you don't see it, you can put a bound, an experimental bound on that. And that happened. And so the simplest versions of this idea of grand unification were excluded based on this, even though nobody's exciting nobody's directly exciting energies at that scale. Now there's a variant that evades these bounds, but it's a very, very useful null result on a parameter in a very interesting theory of physics. Okay, here's another example of a slightly different form. Suppose that I take an electric field. I permeate space with an electric field. But let me stipulate that it's very, very weak, so the energy it carries locally is tiny. And I stick some charges in the system, which also have masses, energies that are small, not nowhere near these high energy scales that we're talking about. Clearly, if I wait long enough, so an electric field accelerates a charge, and if I wait long enough, the system could develop an arbitrarily high energy locally. The energy carried by the electric field is infinite when you integrate over all the volume, coming back to your point from before, but locally it's small. So it's a weak field. And yet, over a long enough time, you could, in principle, access arbitrarily high energy physics. Clear, or any questions? Okay, there's a similar thing in weakly curved geometries with a horizon where the role of the electric field is played by the curvature of the geometry. And one of the features that we're interested in these days occurs specifically in the case of, say, a black hole horizon, in which you drop a couple of observers. So this is a picture, this is a schematic picture of a black hole. This is the same line element I was referring to earlier. And then I wrote it in a way that's useful near the horizon, where, as we discovered earlier, it looks like flat space. And what we're doing here is dropping in two objects at different times, but otherwise in the same way. And the conversion from these, so mathematically, I'll say this in two ways, but mathematically, you can write this ds in this second way by making a change of variables. And the change of variables that's involved in this case is this exponential relationship. So x plus or minus is some prefactor that I haven't written times an exponential in the time t. In units, I should have said before that this r sub s is my notation for the radial position of the event horizon. So there's this exponential relation. And that means that as 1 and 2 drop in exactly the same way, but just at different times, they end up with an energy in this near horizon region, which is a completely well-defined thing. It's a patch of flat space-time. And the energy in the center of mass of the two of these systems is exponentially large in the time difference of their infall. So this took a little more explanation, but really it's a glorified version. It's a space-time geometry or curvature version of this electric field effect I mentioned here. And it's something we'll return to. It's again a situation where the curvature is weak locally, but over long enough time you get a big energy involved. In this case, I should say the energy is distributed quite non-locally, but that will be interesting in this case of string theory. Oops, wrong way. Okay, so in early universe cosmology, so by the way, this whole thing, and I love this term, and so I say it too much, is known as dangerously irrelevant corrections. So these, I said before that the way we parameterize our ignorance is this type of expansion, and these terms that are small at large distance scales or low energies are called irrelevant for obvious reasons. But when you have this situation with long times and or large excursions and or a lot of data, you can get access to higher energy physics. And that basically is called dangerous irrelevance. So in the early universe, such corrections, it turns out, there exist corrections of this kind. In some cases, in the case where this Hubble that we talked about earlier is on the high end, in some cases an infinite amount of dangerously irrelevant terms that matter for the process. This is kind of a spoiler alert. I'm going to explain all of this. But there are sort of two ways that this comes in the early universe. One is that we will see that there's motivation for there having been a phase of accelerated expansion in the early universe. And that is sourced according to these Einstein equations with energy generating the curvature, in this case, the expansion of the universe, requiring a nearly constant source of energy. So as we discussed back here, actually. So we found that if this right-hand side was constant, then we got exponential expansion. And it will turn out that there's a lot of reasons to think that that is what happened in the early universe, and that it was nearly constant for a large period I'll explain very carefully what I mean by the largeness of this time period. The actual time is a fraction of a second, but the universe expands by some 10 to the 26, a factor of 10 to the 26 during the process. And there's a field that goes over a long range. And so there's an important sense in which this is a long process and hence subject to this issue of dangerous irrelevant sensitivity to higher energy physics. The other thing about the early universe is we're getting amazing data more and more, and that's enough, as it turns out, to make tests of various interesting ideas for high energy physics interaction, new degrees of freedom and interactions that might have been going on during this phase of accelerated expansion, including at rather high mass scales that are 2 orders of magnitude higher than the scale Hubble, believe it or not, that we can constrain, potentially detect, but at least constrain using the prodigious amount of data that observers are providing. So for these 2 reasons, in the early universe cosmology version of the physics that we're talking about, in addition to a very simple theory of the origin of structure that I'll explain, it has this added feature of some sensitivity to high energy physics. Okay, so I'm going to move on to that case. Lenny, what is the time scale of this lecture? I wasn't totally sure. So
8:30 is good. 8:30 is good.
Okay.
Longer or shorter, but 8:30 is good.
Okay. No, I mean, I please ask questions if you. Yes.
4 or 5 slides back,
Yes.
You had a slide where you show the energy scales going up
Yes.
and the distance scales going shorter, and then at some point maybe
Yeah.
the black mass, it goes up again.
It goes up again. Yes.
Is there?
Yes. Well, this is a very deep thing, which let me just say a little bit more about it. Although I didn't derive it for you, but what happens when you solve these Einstein equations in the situation where you accumulate a lot of mass together to form a black hole is that the more mass you congregate together, the larger the object ends up being. It's a linear relationship. So this Schwarzschild radius that I wrote is basically the mass times g Newton, or the mass of the black hole divided by the Planck scale squared. Again, I'm setting c to 1. And I'll get into this more in the next lecture, but there's just a beautiful property that this has. Well, maybe I shouldn't go on here, but at the level we're discussing it right now, it's just a fact about these equations that the more mass you congregate, eventually these black holes get larger. The solution gets larger. And so, yeah, it is kind of fun that we measure down here, we measure up there, but not in the middle. Yes?
Are there any higher corrections to the electroweak force as well? And is there any experiment?
Oh, absolutely, yes. So when I discussed this Wilsonian effective field theory, it applies all across the board. So any system you can organize in that way.
Is there any experimental evidence for perturbation in the electroweak force then?
I mean,
Like higher terms?
I wouldn't say so, although one thing that happened before the discovery of the Higgs was something like this, where there were some of these correction terms were very consistent with there being a Higgs boson, even though we hadn't directly observed the Higgs boson. So at the moment, we don't have a situation like that where we can easily expect another particle. But as we went up in energy, that did happen in the past in particle physics. So that's a great question. Any more? Okay. Okay, so let's get started with cosmology. So I want to give you the basic theory first. That's crucial. And again, Some of you saw that beautifully from Leonardo earlier, so I'm going to probably focus on, slightly different aspects of it involving this dangerous irrelevance and so on. But all of this is related. It's a beautiful subject because there are different approaches to it that all intersect in the early universe. So anyway, I'll start with the basics. We'll talk about the expansion of the universe, this idea of cosmic inflation, and a huge spin-off that it has involving quantum mechanics, and this theory that I alluded to of the origin of structure in the universe, before moving on to new tests for other things that might be going on there beyond this minimal theory, including the role of quantum gravity for reasons that I alluded to. And again, this leads to one of the most interesting developments over the last decade, which we've been very into here and has developed in a number of different ways. It has to do with this role that string theory has been playing in empirical science, and I want to explain that carefully. So one direct role that it plays, just to spell it out before we get into details or back into the basics, is that it's a theory. We don't know if it's the right or wrong theory of quantum gravity, but it has a lot going for it. And as a theory of quantum gravity, it accounts for these dangerously irrelevant effects. So it's interesting to model physics that's sensitive to those in a theory that has some account of them. And this turns out to mesh very beautifully with ongoing observations involving primordial gravitational waves. But beyond just thinking of it, taking it sort of literally, it's had a spin-off effect, which is to the mathematical structure of the theory has taught us about mechanisms for cosmology that were just harder to think about in other ways. They didn't occur to us previously, and then that gets incorporated in a more systematic, low-energy description of cosmology, including the observable signatures and the analysis of the data that comes in. So I'll try to get this across, but let's again start from the beginning. Okay, so what's the logic? First of all, we have strong evidence that the universe is expanding. And let me go back to the beginning again before we get to that, just reminding you about a neat feature of light and also sound waves and so on that is called red shifting or blue shifting, the Doppler effect, which is that if you this is a picture of an eye, and if you look at some object that's moving toward you, the pulses of light come faster than if it's moving away or sitting still. And we can also tell how far some object is using the fact that whatever it emits spreads out in space, and so we can relate the intensity that reaches us to where it came from. So this is what led basically to a distance redshift relation, the fact that galaxies, by observation, galaxies furthest away from us appear to be moving the fastest. And despite modern political theory, if I could call it that, let's refrain from placing ourselves at the center of the universe. And if we refrain from that, then we get a picture where just all of space is expanding. Now, I mentioned this Doppler effect a moment ago. I should say next that the expansion of space in itself causes the wavelengths of light to stretch out. And that's a somewhat different effect, but it's similar in that the wavelengths of light change. So more than that, as I've now alluded to a number of times, there's strong evidence for there having been not just expansion, but accelerated expansion that gets faster and faster with time in the early universe. So I'm going to start by explaining some of the early motivations that people had. And actually, the logic of this is a bit debatable, but it's a very interesting argument. And we'll see that there's a lot of reasons for this hypothesis, and it has incredible observable consequences. But let me start from the early motivations again. This is a picture of the universe expanding. This time slice of time is moving upward. The time slice is meant to indicate the present day where our eye is looking. And as we go back in time, things get squished together. There's a particular time slice that's really important for our observations, which is the time at which atoms first formed in the universe, meaning protons and electrons and neutrons came together to form atoms. It's after that that light could just stream toward us relatively freely. Before that, it scattered off these charges. And so we see the famous microwave background radiation from this time. Now, if we were to extrapolate expansion, but not accelerated expansion, further back in time, then the matter in the universe gets denser and denser, and you find, if you just follow those equations, that the densest matter that we understand, meaning we don't go past the Gutt scale or Planck scale, or take your favorite unknown physical scale, and we shut up about what happened before that because we have no idea. So the confusion that comes up is the following. This radiation that have been mentioning, an important thing about it is that it comes to us from all angles on the sky at almost the same temperature. We'll be very interested in the fact that it's only almost the same, but it really is almost the same up to corrections of order 10 to the minus 5. So the problem was, if you take this picture, and again, we're using the fact that nothing moves faster than light. If you imagine that the light's coming to us from one side of the sky versus the other side of the sky is about the same temperature, it's confusing because if you track this back, it looks like whatever the source of this light is, it was never in causal contact within the phase of the universe that we understand using the regular physics we know. That's not a contradiction. There could be a theory of gravity that just from on high dictates that's true, but we wish to do better and really provide an explanation. Another cartoon way of saying why that's confusing is, in normal physics, if two parts of a system are at the same temperature, it's usually because they've mixed up. So if we have a cold tap and a hot tap, they need to mix together to become the same temperature, to become warm. And it's confusing if we're seeing things at the same temperature that never could have equilibrated in this kind of obvious way. So a resolution of this possible puzzle is a period of, instead of just assuming that what we're seeing evolves back without modification, we could postulate that instead there is an early period in which the expansion of the universe was getting faster with time. If you think about it, that means the universe actually is older, because if we fix the expansion rate now, that means that it was slower back here because it's getting faster. And in the same kind of picture, we wouldn't run into the same confusion. There would have been causal contact between the sources of this radiation. Now, this is quite a heuristic argument, but this, among other things, like high energy physical theories with lots of particles that could have been around in the early universe that we don't see, the possibility that the space on which matter is homogeneous could be quite curved, and yet we see it as relatively flat. All of those issues would be also resolved by a process in which the size of space just expanded exponentially in the early universe. Another sort of more prosaic motivation is just that when we write down the possible dynamics that physical theories can have, this source of energy that drives expansion is actually kind of the leading thing you would write down in this Wilsonian expansion in terms of higher and higher inverse Planck masses, say. So it's the most relevant term that we can write down in physics. So it makes perfect sense that we should entertain we should think very hard about the possibility that there was such a phase of accelerated expansion sourced by energy that doesn't dilute, simply for that reason, that it's the most relevant term in the expansion of our Einstein equations. Okay, so we already had this cartoon. Okay, and next, there's a very beautiful spin-off of this that I want to explain. So we know that even if this is true, it can't go on forever because the universe that we observe that Hubble observed and so on is not accelerating. So there's between what I'm calling the early universe and late universe, there's a period in which the expansion is not accelerating that we observe. So whatever drove this accelerated expansion has to end. And so the source of energy that's driving the expansion needs to be there at first, and then it needs to go away. So that means it can't just be some extra fundamental constant. It has to be a dynamical thing. And so the way we understand that, the simplest way that can work in physics, is for this energy that drives inflation to be the potential energy of some new field. We, with great creativity, call this field the inflaton field phi. And the simplest sort of scenario for this process would be one in which it has potential energy that drives this inflationary phase. That's what this early universe accelerated expansion is called. And then this potential energy dies away, and what's left is, among other things, the kinetic energy or energy of motion of the field. Just like a high school physics problem with potential and kinetic energy, this field also carries potential energy and kinetic energy, and it needs a nearly constant potential energy for a sufficient period to do the job of this inflation, but then it needs to end. So we had to introduce a new degree of freedom. The reason I'm harping on that is because once we do that, the moment we add another field, we were interested in it because it could sort of homogeneously roll down the potential hill that I drew in the previous slide and source the early universe inflation, which then ended. But as a new field, it has the possibility of fluctuating, of varying in both space and time. And in fact, in quantum theory, it has to. It can't help but fluctuate. And I'll get to that momentarily, but the idea will be that those essential quantum fluctuations that are an automatic outcome of this hypothesis of having had early universe inflation that ends, we'll get fluctuations due to quantum theory that are perfect. I mean, they seed structure in a way that is the spitting image of the results we get from data. So it's worth emphasizing this before we get to the fancier stuff. Okay, so I haven't said anything about quantum mechanics yet, really, but the beautiful thing about this stuff is it uses really the essential thing about quantum mechanics that I think people have at least heard of. And again, ask questions. Nobody's asking questions. But the Heisenberg uncertainty principle says that if you have some degree of freedom, so let me back up, and we're talking about this field phi, but you could also think about just a particle moving around in some space. So for example, consider a particle that's moving around in a potential well, like this parabola or whatever, some potential well, or just in any system. There's an essential principle in quantum mechanics that says that we can't know its position and its momentum simultaneously. So heuristically, the uncertainty in position times the uncertainty in momentum is some fundamental constant, Planck's constant, which is non-zero. And that applies not just to particles moving around in potential wells, which is the quantum mechanics upgrade of the thing you learned in high school physics, but it applies also to any physical degree of freedom more abstractly, like this inflaton field. It applies to the electromagnetic field and so on. So the inflaton, we can't specify what its field value is and what its field momentum is, how rapidly it's changing at the same time. The best we can do is a kind of minimal uncertainty thing where it takes a normal distribution. So I don't want to, at this late hour, I don't want to bother people with too many equations, but probably everyone's heard of the bell curve and a normal distribution. And basically the simplest theory of these perturbations in quantum theory in a system which will turn out to be relevant for this inflationary stuff, where it lives in a parabolic potential landscape. The best we can do is a minimal uncertainty in position and momentum, which still gives us some probability to find the field at a non-zero value. So this is a little quick, but the upshot, which I may be able to unpack a little more for you next time, is that these fluctuations in the field automatically happen because of quantum mechanics. The probability distribution, the probability for finding the field at a certain value is basically a normal distribution with a width that is of order this constant Hubble that we have in our theory that drove the expansion of the universe. And as a result of that, we will get seeds for structure. So I put back in the numbers that we sometimes set to 1. This is a quantum effect. It's a very beautiful, essential quantum effect. One way to describe how strange it is that the mean value of the fluctuation of the field is 0 in this picture, but the mean square value is non-zero. Okay, so this is the basic picture. It assumes that the interactions that this field undergoes with it amongst its own, the particles that it creates by itself or with other fields that might be around are negligible. And that's something we can push on a lot more. We can test for interaction effects and effects of other fields that might have been around on this probability distribution. But the leading behavior of this fluctuation is as in this normal distribution. Another way to, yes.
Sorry.
Oh, yeah.
With this quantum field, then are there eigenstates that we can maybe measure locally that would pass familiar?
Well, in a certain sense, we measure the. I'm actually getting to that. We don't, we're not back at that time. We're not directly measuring it, but it. Actually, I'm about to say something about that. This gives a theory of the seeds for structure of the sort of the initial conditions. By initial, I mean, say, the conditions at the time when atoms first formed, where this light streams to us. This theory will give us initial conditions on the fluctuations in density in that medium that then affect the light that we see. So that's what we measure. But it fits with a theory in which those initial conditions were set by such a field, which I'm actually about to cartoon sketch for you here. Let me see. Okay. So again, the picture is we have this field that has potential energy and eventually just kinetic energy. It has fluctuations that we're now concerned with. And it's living, it's a field that lives in this exponentially expanding geometry. So let's look at a patch of that geometry of characteristic size of corresponding to the parameter Hubble H that we talked a lot about earlier. So again, Hubble has units of inverse time, and it's a characteristic scale in the problem. And what happens is, a more physical way of describing why it's a scale that matters is the following. So if you think about some fluctuation of this new field that we've introduced over a wavelength that's very small compared to the scale of Hubble inverse, then you might as well be in flat space. The field doesn't know anything about the accelerated expansion to first approximation. It just behaves as in flat space-time theory of fields, which you can imagine we understand pretty well. But as the universe inflates, the wavelength of this fluctuation, exponentially expands to the point where it's quickly pulled outside of this constant, nearly constant, let's say, Hubble inverse patch. So it's actually decreasing a little bit with time, as in this picture, but basically the Hubble is nearly constant, and this wavelength stretches out outside of the so-called Hubble horizon, which is a bit of a abusive language, but this is the picture. And once it freezes out, it stops. It might as well be constant from the point of view of this patch, and the value at which it freezes out is dictated, on average in quantum mechanics, is dictated by the uncertainty principle, and that's the thing that gives us a root mean squared excursion of the field of order Hubble. I think this is a good place to stop. What we'll do next time is to finish the development of this inflationary theory and these perturbations, and get into this business with the sensitivity to quantum gravity, and then also come back to black hole physics and the role that quantum gravity and string theory plays there. So let me stop here.
Eva, before I open up the questions, I want to ask a question. It's a sort of elephant in the room question.
Okay.
There's a whole bunch of things that you obviously assume. And they're the same things I will assume, and the same things that Leonardo will assume. And in fact, they're pretty much the same things that cosmologists and theoretical physicists, experimental physicists all over the world will assume. And yet when it passes through the media, when it passes through the Scientific American, it comes out almost as badly as climate science.
I agree with you. There's that.
Something people believe is wildly contentious. Can you illuminate anything about your feelings about what goes on there?
Well, I mean, should we explain what you mean more? Or there's the public discourse on this subject, as well as on string theory, which we haven't really gotten to, is often grossly inaccurate, I think is what Lenny is saying.
It's not that it's grossly inaccurate. It seems much more contentious from the other side of the horizon than
Right. So right. I haven't really gotten quite to the evidence for this inflationary theory, but it's substantial. And there are those who quite reasonably explore the possibility of alternative explanations of the early universe physics. And that's a perfectly valid endeavor. But the status of that is it's a very challenging problem, and these alternate theories tend to involve physics that is very strongly curved in the sense that I started to explain, and very difficult to understand theoretically. But that has led certain practitioners to, I don't know, to as Lenny is alluding to, write Scientific American articles which are not very accurate. And part of the thing we'll learn a bit, pretty soon in the next part of these lectures is the evidence that there really is for this inflationary scenario. I do actually have more pointed comments to that question that come a bit later after we've developed things further. I feel free to say what you have to say about the elephant in the room, but I'm not sure everybody's read this article, and maybe we shouldn't.
Even news that is not contentious doesn't sell. That's the problem.
Yeah, no, climate science is a great analogy. It's,
Yes, I think it is.
But I just
Yeah.
want to say, your drawings are so clear and so good. No idea what the math means, but they should just sign you up as a visualizer.
well, that's
of
a
this
kind
stuff.
thing. That's a kind thing to say. It's not the reason we believe inflation is the right theory of the early universe. But thank you. Yeah, I'm sorry. Feel free to say what you.
I just wanted to point out that there's a whole bunch of stuff you, I, Leonardo, and pretty much the whole community pretty much takes for granted as having been confirmed, as having been
Well, let me. Okay, let me.
being reasonably solid.
Yeah, let me try and explain a little better what Lenny is saying based on something I did show already, which is, I think I showed it. Okay, so I flashed this thing. Now, this looks like a rather messy plot. What it is a picture of these fluctuations at a variety of scales. The structure that you see in this plot actually has to do with sound waves in the plasma that was there when atoms were first forming, which is very well understood physics. And the model of cosmology that we get that fits with this data, the red curve in these figures, actually depends on only 6 parameters. It's incredibly simple. And that is quite consistent with the simplest theory of inflation, on the one hand, in contrast to what you would get if you just threw a dart at possible ways that the fluctuations could come out. So if we don't know anything about, say, quantum gravity, and we took the picture with the, which I had here somewhere, where things got very dense, and we didn't postulate inflation, but we tried to model what happened in the early universe in some way that involved this dense and highly curved slice of time. You know, we don't know anything about that, and without a theory, we would have to entertain the possibility that there are just wild variations in the fluctuations as a function of scale and so on. The inflationary theory, its simplest versions, is very clear that that shouldn't happen. This is also in contrast to certain other well-defined scenarios like cosmic strings as sources of structure that were viable before this data came in. And just the fact that to good approximation it boils down to these 6 parameters is strong evidence for this inflationary paradigm. In a sense, it's a function that could have had wild variation depending on many parameters, and instead, as a result of that, you can think of it as many parameters have been constrained down to a simple curve that fits with inflation. So it's you can think of it as a function's worth of tests, really. And so there's reasons why we don't just assume it. It is a nice idea, but we don't just assume it. It has a lot of evidence in its favor. Of course, you never prove a scientific theory, you just get better and better evidence. And so far, inflation has survived these massive tests extremely well, despite what you might see in the scientific American level literature, which tries to, it sometimes appears as if there's a sort of 50-50 probability between this and some other scenario, which is, much more challenging to develop and has not had such successes. At least that's my view. So, Xiaoliang.
So, assume that if I have not one infinite number of many, or some number of components in them,
Yeah.
then let's say it's still zero. But can we tell the difference?
Yeah, that's a wonderful question. Yeah, I'm glad you asked, because I'm going to get to that more next time. But these, let's see. So we've gotten to these fluctuations, and we discussed how if you assume there's only one field and it has no interactions that really matter, it's just a bell curve. But we can do tests on the light that we see eventually that has imprinted on it the size and the statistics of these perturbations, and we can check for much more elaborate functions here that could come from other fields. You know, it's very natural to expect other fields in physics when we complete our theories of particle physics and gravity. The ways we understand how to do that involve extra fields, and one of the things we're dealing with now in collaboration with Leonardo and others is exactly that. Even very heavy fields make an imprint on this picture that change the statistics a bit, even if they're 2 orders of magnitude higher than Hubble, but interact with the inflaton at a reasonable strength. They lead to effects on this picture that we can either constrain or potentially detect, and that is in progress. That's a very current area of research. There's other versions of this involving multiple field sectors, others of which could be light, and that also makes an imprint on this sort of picture. So it's a great question, and I'll try to. I'll definitely get to that next time. Yeah.
I was just hoping you could explain the picture that you have, like the ball rolling downhill.
Yeah.
The ball is hit inflaton potential.
Right.
I'm having a trouble just kind of truly understanding what is like the x-axis on here, because it seems like it could be time, but then it goes up again and gets stuck at the bottom.
I'm really glad. I'm so glad you asked that. So the horizontal axis here is the field. This is so the field is some degree of freedom that can have a strength. So that's what this phi refers to. And I should have labeled it, but the horizontal axis is that field phi, and it's changing with time. It's rolling down this potential. Now, it's true that we can measure time using the field itself as a clock, and that is actually a very useful way to think about the problem. I'm going to get to that later, so let me actually, I'm not going to go on, but there's, since you asked the question, there's sort of 3 ways you might think about measuring the duration of inflation. One is how much the universe expands, which turns out to be a gigantic factor of 10 to the 26th. Another is how far does the field go, and it's a perfectly good measure of time as well. And that turns out to be the way to think about it to understand the connection to quantum gravity best. And then, the time coordinate t that we've been working with, in that variable, it's just it's a fraction of a second. So all of these statements are true. It's the same. Yeah. So see, they're all true. It's just different ways of measuring the extent of the process, and the top and bottom are kind of the most useful, and I think sort of the most faithful ways of thinking about it. But they're all true. Yeah. Yes.
Yes. I've recently been reading a series of treatises by Andrew Thomas, in which he proposes a revised theory of gravity, which inside of a black hole or any collection of objects which is massive enough to have a Schwarzschild radius, he proposes that inside of a black hole that mass becomes negative. I'm sorry, he proposes that gravity reverses and becomes repulsive. Now, this doesn't make any sense to me unless inside the black hole that also mass is negative. Well, recently there's been a report at Washington State University that they produced in the lab a fluid with negative mass. You apply a positive force to it and it accelerates in the opposite direction. Does all of this have any relevance to what you're saying?
I would have to look at what you're referring to with the experiment. I'm not sure what that might mean, to be honest, but maybe you can explain afterwards. Sure. There are these kind of laboratory analogs of black holes called dumb holes, in the sense that it's sound waves that can't get out. But if you ask the question, okay, we have this mass parameter when we think about black holes, and if you just say, mathematically, what happens if you make that negative? It causes a problem. There's a certain kind of singularity that you get in the solution in that case, which is very difficult to resolve. It probably is not possible to resolve it, and the reason we think so is that if you know, well, first of all, we don't understand, we don't understand how to resolve the singularity that the Einstein equations would imply. But more importantly, if you had negative mass objects, then things would be very unstable in physics generally. You could pair produce them and decrease the energy, ad infinitum. So there are good reasons why the negative mass Schwarzschild geometry doesn't make sense. Yes?
You said that in the beginning, you said that it takes an infinite amount of time for something to get to the horizon. So does that mean that singularity never forms?
I am not sure what you mean by infinite amount of time. But the thing about horizons is that nothing gets out of them, so,
You said an infinite number of clock ticks, I guess.
Sorry, yes. Okay, so
if the matter never reaches the horizon, it takes an infinite amount of time, I would think the singularity never actually forms.
Well, the thing is, if you're falling in, it's an arbitrary thing what your clock is doing in some sense. And if you're falling in, the proper time does not build up at the horizon. It just, according to the classical theory, you just go straight through. So the question of how to put together these different observers' views is a very interesting one that we deal with. But at the level you're asking, it's not that the singularity is unimportant for the infaller in the classical theory. Yes?
So when you're talking about the idea that the inflaton field is some sort of exists as some kind of potential and then becomes this energy, but then you had a drawing where the inflation slows down again. So is the notion that somehow returned to the energy of the field, or is it dissipating by some other mechanism?
Well, that's another great question. So it's a little of both. So if all we had was this inflaton field rolling down the potential, then the potential energy would basically become kinetic energy. That's a little quick because in the expanding universe, the energy in the phi field isn't strictly conserved by itself, but basically it would go into the kinetic energy of the field, so to speak, its variation in time. But in a complete model of inflation and its aftermath, there's a phase called reheating where we have to excite the particles that we know and love that we're made of. And so, at some level, the inflaton couples to those degrees of freedom, and as it rolls down, it imparts energy into them. And that can work in a wide variety of ways. It's an area of modern research in this subject, but that's the short answer.
Okay, go ahead.
Could you give us a history lesson? There are two interesting experimental results that have come out recently on some scale. The gravitational waves and the expanding universe. What was your life like, before those?
What was the second thing?
The expanding universe.
Maybe do you mean the dark energy, the accelerated expansion?
Yeah, sorry.
I'm not quite that old to have lived through the discovery of the expansion itself, so the discovery of the dark energy was gigantic. It's a wonderful thing. It's a single number so far, at least, and we suspect that's it. But it's a single number that changes. The fact that it's non-zero and positive means something for the causal structure of the whole space-time. So it was a huge discovery. And I may be able to say more about it later. What was the other one you wanted to? I'm not sure. Gravitational waves, yes. So that's also a beautiful, beautiful thing, of course. Well, I don't know what to say about it. It's hard to overstate how exciting it is that this LIGO experiment managed to detect, this process, this event. For my own interest in early universe cosmology, there's another version of gravitational waves which is very much in play, which is the primordial version. And that we test for using a slightly more indirect measurement involving this microwave background radiation. And I'll be able to talk a bit more about that next time. And in that case also, there's an interesting threshold that we'll get to. Either we'll see it by that threshold or we won't. And that will tell us whether this inflaton field, in fact, it's right here, whether this inflaton field moved over a range that corresponds to bigger or less than this huge Planck scale. So it's a wonderful observational constraint to come from gravitational waves of a different sort. So, yeah.
The way I understand what I learned in this class here about the slow inflation turning into a reheating, that there is some kind of a runaway conversion of potential energy into kinetic energy. And I mean, what is the physical intuition of why this conversion runs away?
Well, it shouldn't actually run too far away. It just, I mean, you've got it. You've got the right idea. We have potential energy, and then it converts into kinetic energy with the added point that it.
What triggers it going into that?
Just the potential dropping. I mean, it's just like a particle on an inclined plane from.
Okay, so based on the field value, the potential just happens.
Exactly. The field value is a physical degree of freedom that is, similar to the position of a particle on an inclined plane, right?
When you go over the edge of a cliff, your kinetic energy tends to increase.
Yes.
In that case, was there a long period before this triggered inflation, before the thing fell off a cliff?
Well, yes. I mean, that's what I'm trying to express here. So it's okay. In this variable t that we've been talking about, it's a fraction of a second. But there are two better ways to really think about how long or how extensive the process is. This first one is, how much did the universe expand? And it expanded by this ginormous factor of e to the 60 or 10 to the 26th. That it sort of scales with Hubble. I'm giving you the extent of it on the high end of Hubble. And then again, we'll get into this next time, but another measure of how long it goes is how far the field rolls on this potential. And that, we don't know. There are different ways the process could work in detail that have different answers to that question. But in all cases, there's a sensitivity to quantum gravity that I want to get to. And it's again to me, it's a more useful measure than the fact that this delta t is a fraction of a second.
Okay, let's thank Eva.
For more, please visit us at stanford.edu.